Okay guys, so in this section we're going to continue our discussion of limits. We're going to start evaluating limits analytically. So first of all, we'll define some basic limits. Okay, so first we'll start with some three basic limits here, and this can be derived intuitively just from their graphs, and also can easily be proven with the epsilon delta definition. So think of B and C are real numbers, so there's some constants here. So for instance, for the first one here, the limit of any constant at x goes to some limit point C, that's equal to B, right? Because if you think about the constant function, it's just some flat horizontal line. There are no holes, nothing, no breaks in there. So no matter what your C is, your function value is always B. So that should be pretty straightforward. Also, limit of x, function x, as x goes to C is equal to C. In other ways, you can think of just substituting that C into that x. And that's pretty clear too, because x is just a line that goes through the origin. It has slope 1, right? So then, again, no holes, no anything. We have built our intuition on functions like this. So it should be pretty straightforward here that the limit is just C, right? So it's like you evaluate the C at this x. And then similarly here, if you had that x raised to some power, and in other words, a power function, what we call that, which is a special case of a polynomial function, then it's just as x goes to the limit as of x to the n as x goes to C, it's just that C to the n. Right? So those, again, I'm not going to go into the proofs or anything. You can do them yourself as practice, or look at your textbook, have some of those proofs, and they're pretty straightforward, but things that we're going to use all the time, and we're going to build our rules on top of these. Okay, so here are some examples quickly. They have the limit of 3, number 3. As x goes to 5 is equal to 3. So again, this is a constant no matter what x is going to. You know, this could be any other number. If this is a constant, it's always going to be the limit is always going to be that constant 3. If we take the limit of x as x goes to 5, so then the answer is going to be the actual limit point, right? As x goes to 5, this is just what we call in algebra the identity function, right? So then where the input and the output are the same. Right, so it's like you're plugging that 5 in for x. And very similar here, if you have that same x raised to some power, as x goes to some limit point, in this example is 5, you just plug in the 5 in there, and we get 5 to cube in this case, because we're doing limit of x cubed, and then that's of course 125, and that's the limit. So very straightforward here. I should be able to quickly do any of these basic limits. Next thing is a property of limits, and all of these are presented as theorems here. The basic limits, property limits, and some of the things we'll see after this will be theorems, because all of these could be proven with the epsilon delta definition. And you know, for the sake of time, we're not going to be doing all that. But again, all of these are pretty straightforward. We have that B and C are real numbers, n is a positive integer. So if we have a limit of a function f and g are functions with limits here, and they already exist here. So we say the limit of f as x goes to C is L, limit of g as x goes to C is K. So let's say those limits exist, then all of these properties are going to follow. The limit of a multiple of this function f would be equal to that multiple times the actual limit, right? If we add the limit, if we do the limit of the sum of two functions, since we already know these two exist, then we can just add the two limits. And same thing for product, same thing for quotient. Of course, understood that k is not equal to 0, so this is not undefined, and also for a power. Okay, so very important here. Even though these are very easy to understand, you can kind of just read through them and see how they work. It's very important you realize that in order for these 5 to work, these 5 properties to work, these two limits have to exist prior to. Okay, you can't do this if you don't know that these two limits exist. Okay, so that's the only thing that's important here. because that's the kind of like the condition here, the part that is supposed to be given. Okay, so if it's not given, you need to figure out whether before you used or before you apply any of these properties, you have to make sure these limits exist to be able to do this. Now, the next thing here is limits of polynomial and rational functions. This theorem is pretty much saying, because you remember from your algebra, polynomial and rational functions are really nice and continuous. This word continuous we're going to use later in the next section, but basically don't have any breaks or holes in their domain. Now, for the rational functions, we know that we have some asymptotes there, but other, where there's not, we don't, the domain is not defined there. The function is not defined as those asymptotes. So, but other than that, on everywhere else on their domain, as long as it's defined. Okay, so since these functions are pretty nice, we're going to be able to apply direct substitution here. So you can see how if we take the limit of a polynomial function as x goes to some c, some number, real number c, then that's going to be equal to the polynomial evaluated at that c. Because again, we said polynomials are really nice, smooth, there's no holes or anything. We're able to plug that in and just get the limit. Right? We don't have to do anything else. This is what we call direct substitution. Now, same thing is going to happen for rational functions. We just got to make sure that this c, it's in here in the domain of the rational function, and then of course this to have this limit exist, we have to have that q of c, which is the denominator here, is not equal to 0, right? So for polynomial, when we evaluate polynomial or rational functions, we're just going to be able to substitute directly and then get that limit. Okay, very similar for function involving a radical. So the limit here is going to be valid for all c, this limit point all c, when n is odd, right? Because we're able to compute that root without having complex or imaginary or anything like that. But when we have n even, we have an even root here, then that's only going to work for when the c is greater than 0, so it's positive, so that way we're able to get a real limit, right? Because remember, the limit is a real number. If it does exist, it'll be a real number. So, with those restrictions, yeah, everything is going to be a direct substitution as well. Okay, another property that we have is the composition of functions. So again, all of these are stated as theorems, again, because they can be proven, but they're pretty straightforward. I'm going to start using them in our problems here. The limit of a composition, a composite function, is equal to the function, the outer function of the limit of the inner function. And it's saying here, if that already exists, right, we can substitute that limit in there, so that becomes the input of f, right? If the limit of g of x as x goes to c is equal to L, as if we stated here, again, this has to be given, or you have to already know that this exists to be able to apply this property. Then that's equal to the function f, the outer function f of L, that limit. Okay, so we've seen how the algebraic functions can use direct substitution to find limits. Well, for transcendental functions, we'll have something similar, since they're also, at least the ones that you should be familiar with, are also nice. You have here the limits of transcendental functions are just evaluating the limit point on the function itself. Right, so if you think about the graphs of all these functions, they're smooth in their domain. So like sine and cosine, they have all reals of domain. Then tangent, all the other four have asymptotes, but of course we don't have anything going on at those asymptotes because they're not part of the domain. But everywhere else, assuming this c is in the domain of the given transcendental function, then we can just use direct substitution and get that limit. Same thing happens with exponential and logarithmic functions. As long as that c is in their domain, we're going to be able to substitute directly and find that limit. And there's one more thing that we already talked about, is the functions that agree at all but one point. If you remember the functions, when we started talking about limits and started building our intuition as to what a limit was, we saw functions that were identical to other functions except for one point, right? We had a hole at one point. So that's basically what this is saying, right? And we determine how, even if there's a hole there, the limit, it still exists. As a matter of fact, it exists if you have just a hole there, because you're constantly getting closer and closer to that hole. So there's a value there, but it's not defined on the function, right? Or it may be defined somewhere else. So the limit still exists there. Therefore, if you have a function, what this theorem is saying pretty much is summarizing what we've already talked about, that f of x is equal to g of x for all x except some c, right, which is gonna be our limit point here. So if it's exactly the same everywhere else except for that c, then the limit is going to be equal of f of x is going to be equal to g of x at that c. And remember, this only works if it's just that one point. In other words, you have a hole right there at x equal to c. So with all these properties and theorems, I mean, you're able to find a lot of limits right away just by direct substitution here, right? So if you encounter any of these limits, you're welcome to use any of these properties, any of these theorems to find those limits, right? Don't need to use any fancy technique. If it satisfies any of these conditions, right? We have any of these functions, and the limit point is on this domain, so you don't need to do anything other than just substitute it into the function and find that limit. What I want to do now is discuss some of the techniques for finding limits analytically. So there are some common techniques that are used to find some limits that we are not able to find with our basic properties, right? With the properties and the basic limits that we already have. So in this case, for instance, this is a rational function, right? And we're going to we already know we have a property that says that I can substitute this limit point into the function, as long as this is in this domain. But this -3 happens to be not in the domain. And if we plug that in, right, you see that right away. If you plug that in, you will get 0 over 0. For that reason, that's indeterminate. Now, that doesn't mean the limit doesn't exist. So remember, the last property here said that if we have a function that is identical to the given function, that the one we're trying to find the limit of, except at one point, we'll be able to find the limit of that function. If we compare it, right, it's actually going to be equal to the limit of the other function, the identical function. We're going to try to do that, and this is what we call the dividing out technique. You start by factoring. So I'm going to start here, factoring the rational function. Okay, so we have now this limit of the same rational function but factored top and bottom. And notice how we have a common factor here. So we can simplify this. This x plus 3 goes away, and we end up here with the limit of x minus 2 over x minus 3 as x goes to -3. And notice how this is the case where we found a function that is identical to the original one except at x -3, right? X equal to -3, but we are now able to plug in, direct substitute this -3 in here, and we're going to get that this is equal to -3, so we can substitute that x for -3 minus 2, -3 minus 3, and we end up with -5 over -6, which is just 5/6. This dividing out technique comes really handy when you have a common factor here. So the idea is to, when you have a rational function, always factor top and bottom, and we already know that there's a hole in there, right? If we were to graph this rational function, there's a hole, but the limit still exists. Whether there's a hole or not, the limit will still be the same number. So another example here deals with radicals, and we're going to bring our skills here of rationalizing. Now, typically when we rationalize a fraction is when we have a radical on the bottom. So that, because in math we don't like to have a radical on the bottom, we go through the process of rationalization to, rewrite that expression so that the radical is not on the bottom. Well, here we don't have a radical on the bottom, we have it on the top. But this idea of the process of rationalization is going to help us rewrite this expression, this function, in a different way, so that we're able to plug in this or direct substitute this limit point. So notice here how, okay, if I try to do this by direct substitution, when I plug in the 4 in here, I get 4 plus 5 is 9, square root of 9 is 3, minus 3 is 0, and then I also get 0 on the bottom. So again, gives me that 0 over 0, that indeterminate form. Because it's called indeterminate, guys, because it leads me to no conclusion. Doesn't tell me, it's not a number, it's undefined, it's indeterminate, but it doesn't tell me whether the limit exists or not. We have to investigate further to be able to determine the limit here, if there is a limit. Okay, so the idea here is we're going to multiply here this function by square root of x plus 5. And instead of minus, it's going to be plus. We're going to use this sort of conjugate idea that we had in algebra when we were dealing with complex numbers. But this is the idea of rationalization, and we're going to do the same thing on the bottom. Yeah, remember that whatever you multiply on the bottom, you got to do it on the top, or top and bottom has to be the same so that you don't change this expression here. So that when you go through that multiplication, we're going to go ahead and distribute those two binomials. You're going to get a difference of squares here. So you'll get the square root of x plus 5 squared minus 3 squared. And on the bottom, I could distribute that, but I'm going to leave it as a product. So remember, you're still taking the limit as x goes to 4 here. All right? So then if we keep going here, right, keep writing the limit. Don't drop the limit here. We haven't done the limit yet. The square is going to take care of that square, and we end up with x plus 5 minus 9. And then we still have this whole thing on the bottom, right? So we're going to write it again. Okay, so notice how I end up with x minus 4 on the top, and I already have that on the bottom, so I can cancel those out. So I end up with just 1 on top. And so it was a good thing that I didn't distribute this on the bottom here, so it was easy to cancel the x minus 4. And I still have this square root of x plus 5 plus 3. And then now I'm able to, because this is no longer a minus, I now can plug in the 4, and that gives me 1 over square root of 9 plus 3, and that's 3 plus 3 is equal to 6, so this whole limit is 1/6. Okay, so this rationalizing technique is very typical, common technique that is used especially when you have radicals. So these two techniques are the most common ones here to finding limits analytically. So we have the dividing out and the rationalizing technique. So we're going to be practicing more problems, more exercises with these two techniques. One last theorem I want to mention, or one last main theorem here is on this section is the squeeze theorem. And so a squeeze theorem is going to be a theorem that will help us find a different kind of limits. So it basically says, if we have 3 functions in this order right here, so 1 is greater, so we're going to say f of x is greater than h of x, but less than or equal to g of x. So greater than or equal to h of x. So it's right in the middle, right? And this is where the name is going to come from, squeeze theorem, also called sandwich theorem. So this is true for all x in an open interval containing c, except possibly a c. So you're going to see a lot of this except possibly a c, because remember, it doesn't have to be defined as c. There could be a hole there, and still the limit exists. So that's why you always get that part. And if the limit of h of x, which is the smaller function there, as x goes to c is equal to L, and the limit of g of x, which is the larger, or the bigger function here, as x goes to c is also equal to L, then that means that the one in the middle, f of x, the limit of f of x as x goes to c exists, not only exists, but is also equal to L. And intuitively, this should make sense, guys. So if I was to make a graph here, just a rough sketch of the idea here of the squeeze theorem. So it's basically saying if you have an h of x, so let's say you have some function here, and let's say this is your point C right there. So we know, and this is L, your limit is going to be L right there. And then you have another function. So again, we're going to say this is h of x. And then you have a g of x that is larger, right? Larger function, some g of x there, right? Where the limit of g of x as you go to c is also L. So then any function in between, right, those two functions, the limit of that function would also be L. And that makes sense, right? And that's also hence the name squeeze theorem or sandwich theorem, because that function f is being squeezed by the other two. So then that forces the limit of f of x as x goes to c to also be L. But again, you have to have these conditions here, right? So there's two conditions. This right here, for all x in the open interval except containing c except possibly a c, and then this two limits have to be equal to L, right, of the two functions, the smaller one and the larger one. So that way the middle one, the limit of the middle one would also have to be L. That limit will also have to be L. So just that's kind of like roughly what that theorem is saying. So I want to use this theorem to prove one special limit. So here's my special limit here that I'm going to try to find. And notice how right away, this is definitely not one of my basic limits that I can figure out or that I know, on top of my head. If I start using the properties here, you may say, well, can I just do the limit on the top, limit on the bottom? Yeah, but remember, to be able to use those properties, you have to be able to know that these two limits exist independently. So the one on the top and on the bottom. So if we go back here, limit of sine of x as x goes to 0, yeah, that exists, that's 0. And the limit of x as x, that's 0. But remember, that worked only, for the quotient one, it worked only if that k was not 0. So I can't, unfortunately, that would have been nice, but I can't use this quotient property because that k is 0 there. So then that's out of the question. I can't use any of those properties. If I start thinking about I can't do the rationalization technique because I don't have a radical. I can't use the dividing out technique because there's no common factors to get rid of here. So then I'm going to have to use some other technique here. And so this is where I'm going to be able to use the squeeze theorem. Now, to be able to use the squeeze theorem, I'm going to have to set up the conditions here. I need to make sure that I have these two conditions first, the inequality and that the limits, these two limits are actually the same real number. So we're going to set it up, and I'm going to make a geometrical argument here. Okay, so here's the idea, guys. So if we have a unit circle here, and you already know that unit circle is radius 1, so this is what we have here, and just for the sake of argument, make it easy to see here. We're gonna stay here in the first quadrant, and if we let theta be here in the first quadrant, we already know, because this is a unit circle, this point right there are cosine comma sine of theta. Cosine of theta comma sine of theta. Now remember, if you remember you're in a circle, that's what it is. Now, if we project or kind of draw this bigger right triangle here, all the way over here, this point right here happens to be 1 comma tangent of theta. And this shouldn't be too hard to see. If you see that one side of that right triangle is 1, the other one can be derived in relation with this theta. This has to be, this side, this length right here has to be tangent of theta. Why? Because tangent is opposite over adjacent. So if I were to do tangent of theta with respect of this triangle, this big triangle here, right triangle, then you'll have opposite over 1. So whatever this opposite is tangent of theta here, because that's 1. Okay, so then I can say this coordinate then is 1 comma this height is tangent of theta. Okay, so the idea is going to be the following. So we have here 3 sections, right? From this sketch that we had here on the left, we have that if we compare the areas of these 3 sections, or 3 regions here, we're going to come up with the inequality that we're looking for. First of all, look at the big triangle, and we see that we know that the area of triangle, any triangle, is base times height divided by 2. We know this is 90 degrees, so then this tangent of theta is the height. So then tangent theta times 1 is tangent theta divided by 2 is tangent theta over 2. So that would be the area of this triangle here. Now the area of the sector, there's a nice formula for it, is 1/2 the radius squared times the angle, the central angle. Well, the radius is 1, so 1 squared is 1. 1/2 times the angle times 1 would be theta halves, right? So whatever the angle is, so that's the central angle. And that would be the area of this sector. And then finally, the area of this triangle, the smaller triangle here that we had here inside this sector, would be, again, base times height. The base here is 1. So this is 1 here because the radius is still 1. That's still the radius there. This is the same side, guys, if you haven't noticed. This side is the same side as that, the same side as that. But now the height of this triangle is sine of theta, as you saw here from the coordinate order pair here. Sine, that y right there, that's sine theta. So then, again, just like we did on the first one, this first triangle, that we base times height. So base 1 times height sine theta over 2. So that gives you sine theta over 2. Now, clearly you can see this triangle is, this area of this triangle is bigger, it's larger than the area of this sector, right? Because the sector is contained in this triangle. And then this sector is bigger than the area of this triangle here, as you see this triangle contained inside the sector. So we can go ahead and say that these quantities compare in the following way. So we come up with this inequality. Now we still have to do some work to this to get it to look like the condition of the squeeze theorem. So then we're going to do some algebra in here to manipulate this inequality here in the following way. Okay, so I've written the inequality over here, and we're going to start doing some things to it here to be able to get it to look like the condition from a squeeze theorem. So the first thing we're going to do is, we already know this is true. We're going to take the whole inequality here, and we're going to multiply it by 2 over sine theta. Now we have to do that to each one here. We're going to get that, well, this 2 cancel out, and tangent divided by sine is going to give you a nice 1 over cosine. So let me write it over here. You're going to get a nice 1 over cosine theta greater than or equal to, the 2's cancel out here too. You get theta over sine theta greater than or equal to, you're going to get a 1 there. Okay? Because these two are reciprocal of each other, so when you multiply them, they cancel out. So we get this right here. So we almost get that middle part to look like this. We just have it flipped here. We have it the reciprocal. So to get it to look like sine x over x, or sine of something over that same something, we're going to flip everything here. So we're going to take the reciprocal of this. Now when we do that, automatically the inequality signs are going to change direction. So if we just take the reciprocal, switch everything here, all the 3 quantities here, we're going to get cosine theta, and now this is going to change. Now this is sine of theta over theta, and then 1 over 1 still 1, so we get our 1 there. So we finally got what we're trying to accomplish here. And notice how our function to the left and our function to the right happen to be really nice. So then we have the first condition of the squeeze theorem right here. We got this part. Now we need to show this before we can conclude or use the squeeze theorem here. And that happens to be pretty straightforward here, because I know, these are just from our basic properties, our basic limits, I know that since limit as x goes to 0 of cosine of x is equal to 1, we can just substitute that in there, because this is, remember, our transcendental functions. We can just do direct substitution there, and cosine of 0 is just 1, so that's its limit. that happens to be equal also to the limit as x goes to 0 of 1. This is just a constant. Remember our very first basic limit here. The limit of a constant is just that constant, so it's 1. Since this is true, this satisfies the second condition of our squeeze theorem. We had this, we had the second condition, so therefore we can conclude, use the squeeze theorem and say therefore the limit of the middle function, right, this right here, this function right here, which was a function of interest here, sine of x over x, as x goes to 0, is also, must also be equal to 1. Okay, so this concludes our proof of that special limit here. And so this gives us the first of 3 special limits here. We just proved the first one here. So again, we already know this is 1, and you had the nice proof in here. Number 2 is actually going to be proven by using this one here. So again, we already proven this one. We can just use the result to prove something else and do a little bit of trick, verification, manipulation here. So number 2. As a matter of fact, we can quickly do it and we'll finish with that. Now, number 3, it's one that you just want to know. Unfortunately, we don't have the background to prove it right now or to derive it, but we will be able to do this, a limit like this, later on. I think it's chapter 3 or 4, we'll be able to apply a different technique to be able to do this limit. But let's finish with this number 2 here. So we just proved number 1, and so let's do this limit here. I can use the substitution, direct substitution. You would say, well, can I use the squeeze theorem? Maybe, but there's an easier way. Now that we've proven, or we have this limit, that first one here, limit of sine x over x equal to 1, we can do some manipulation to this one using some trick, and we're going to encounter this one in there, and we'll be able to use this result. So in the following way. So if you remember the conjugate idea, I'm going to multiply here top and bottom by 1 plus cosine x all over 1 plus cosine x, so same thing, okay? So I'm gonna get that the limit is still the same thing as x goes to 0 of what? Well, when you distribute this, the numerator, you're gonna get 1 minus cosine square x, right? All of this divided by x 1 plus cosine x. So I'm gonna keep it in the factor form on the bottom here, because you'll see what I'll do in a minute. So this is equal to, we're still doing the limit as x goes to 0. Notice how the whole point of doing this in trig was so that we can use that Pythagorean identity. And if you recognize this, remember how the top is equivalent to sine square x. This is from your Pythagorean identity, right? And again, I still have the same thing here, 1 x times 1 plus cosine x. Okay, so here's the trick. I'm going to go ahead, split the sine squared into sine x times sine x. I can do that because sine squared is just sine x times sine x. So I'm going to do sine x times sine x, and all of this is divided by x times 1 plus cosine x. Okay, notice how I purposely left this. I didn't distribute the bottom because I think you can see it now, right? Notice here we have the special limit that we just proved, and this part right here, the other part, is just going to be really easy to evaluate, right? So this is a product. Now, can I use my property here to split it? So if you go back to what we went over here, can we use this product property where we can split it and just use a limit? Yes, as long as these two limits exist independently. So do they? Well, let's put them apart, and then we'll actually confirm that they actually exist. The limit as x goes to 0, sine of x over x, times the limit as x goes to 0 of sine of x over 1 plus cosine of x. Okay, does these two things exist by themselves? Well, we know this one does, right? The first one. We just did this one on our last problem, or exercise, example. So this is equal to 1. So that's a real number. And this limit right here, can we just use direct substitution? Well, sine of 0 is 0. Cosine, as long as we don't have 0 on the bottom, we'll be fine. Cosine of 0 is 1. 1 plus 1 is 2. So 0 divided by 2 is 0. So that's like a real number. So then therefore, we're going to be able to use the property because those limits exist. Yeah, this is 1 right there. And this right here is our 0. So then this whole thing is equal to 0. Therefore, proving that this limit is in fact equal to 0. So notice how it was very straightforward once we did a little bit of trick here. Did the conjugate idea, use the identity here, split it. So, you have to kind of use your imagination there a little bit. Now, it doesn't mean this is the only way to prove it, but it's the simplest, most straightforward way, and it relies on on a result that we just we got previously, right? Namely this first special limit. So we already have that. So having that result makes this really easy, because if you didn't know this was true, then you can use it and you'd be stuck there. And then of course this one is just direct substitution. So 1 times 0 is just 0, so then the whole limit is 0. Again, we're able to use that product property because these two exist. If one of these was undefined, so then if we don't know that this exists, I'm not able to split it into a product like this. But since we do, and we proved it in the previous example, then I'm able to not only find or use the property of the multiplication, split it in this way, but I'm also able to find the whole limit. And so we prove it in this way. We've showed 1 and 2 here from these 3 special limits. Again, the third one is a very common one too, but we'll be able to do it later on with a different technique.